Greetings, everyone. My name is Hagen, and now I am trying to present my paper regarding FreeCell strategies on basically uh, a solver using the A-star algorithm to develop a FreeCell solver. Let me present the paper to you. Okay, here's my current paper regarding this FreeCell solver with best first search via custom heuristics. So first of all, let's go into the introduction on why I decided to develop this FreeCell solver instead of other projects. The first thing is that the game of FreeCell is a very well-known variant of solitaire. It is distinguished from other variants by its nature as a game of skill rather than luck. Because a game of FreeCell already has a fixed structure from the start of the game, there are no random variables that we don't know about the game yet, so that this configuration can be immediately solved without any random variables that are probabilistic. So the game of FreeCell is deterministic. Because of that, I have decided, you know what, a solver is quite proper for a FreeCell type of project. I am quite interested to actually build one. So I have built one with the A-star algorithm. So why do I decide to build the FreeCell solver with the A-star algorithm? It's because the A-star algorithm is a best first search algorithm, which finds the best possible path on continuing the iteration, and it is quite guaranteed to solve the shortest path to the solution. So the A-star algorithm in this FreeCell project is actually quite key to overcoming the problems of the vast memory state that may be a depth first search or a broad first search type of iteration will not be able to actually traverse all of its nodes one by one. So it is actually key to the memory state problem. Okay, let's go to the theory. So the theory pretty much consists of the FreeCell rules. Then there's the A-star search on what is the A-star search. It's basically a function where Fn is Gn plus Hn, where Gn is the path cost currently and Hn is the heuristic cost. All right, let's just go to the solver implementation. So in the solver implementation, I have several different components actually. Let me share my actual source code. So in my actual source code, uh, there are several different components. Namely, the first one is the main program, which runs through all the programs, runs all the modules. It imports all of these. Then there are certain utilities like the board loader. It reads from the txt file. Then there's the search functions like the A-star queue. It uses a priority queue. It's the search algorithm. Then there's a private module for the heuristic function. Actually, there are many different kind of heuristics as I explained in the paper. And then there's the node module, which is actually an object-oriented module. A node consists of a game state and a solution state. Solution step, I mean. So the game state actually models what the game is like after a certain step, while the solution step actually stores the data, like in an X amount of turn. What does the player have to do? What is the current movement on the turn that will be printed out during the solution pathfinding. Well, when the solution is actually found. And then, yeah, this is the solution step. Basically, FreeCell also have rules on its own, and because of it, it is actually a constraint to the uh, heuristics too, and like the what potential moves do I need to actually traverse from one node to another node. There are certain restrictions that are implemented in the rules function. All right. Then there is the models, which are the basis of this game. It's a card and also a game state, which consists of a list of stack of cards in tableaus, in the free cells, also the home cells. I mean, that's basically it. Let's go back to the document, I guess. Yeah, and this part is actually what I previously mentioned. There are certain heuristics that are already implemented. These are custom heuristics with 5 different criteria. Let's just go to the test cases. So for this paper, I have decided to actually implement and test several categories of tests. The easy one, the medium one, and the hard test cases. For the easy test cases, uh, pretty much the easy test case is an easiest test case problem for FreeCell solvers, which is game 25904. This easy games here are defined that for games that doesn't require the use of free cells to be solved. So pretty much, yeah, we can just try to run it on our code. But before that, I want to also explain about medium games. So here I define medium games as the hardest easy game and a random, literally random game. So after all these tests are conducted, there are also hard games, hard games that ones that require at least a minimum of all 4 free cells to be completed. It is not an easy task because, to select moves, there are combinatorics for the potential moves. So on a certain depth, it is very, very complex if you didn't implement the heuristic algorithm. Not the algorithm, I mean the heuristics to judge the ordering of the queue. So I have also selected a very hard game with a minimal moves required as in 50 moves right here. The least known minimal moves for game 5087 is 50 moves. And then what else? All right, let's just do the testing right now. So for testing, you can actually compile with something like this. So you compile it to the bin folder. Okay, before we solve, this is the easy test case. As you can see, when I load it here to the solver, it immediately provides an output like this. The output is consist of the early game state, then does it found a solution? If it finds a solution, it will detail the solution path like this. And as you can see quite clearly, this is a valid solution path. You can try to test it on your own. Okay, 34 moves for the easy one. Let's go the second easy file. Let's try it. Yep, 25 moves, although it has a minimum of 18 moves. That's quite interesting. But for now, let's just skip it first. Okay, let's now try to the medium level file. As you can see, these tests have already properly been conducted and actually are already added to the paper. 80 moves, it's not ideal, but actually it technically does find a solution, so it's still valid. And for the medium level test, it actually needs 58. All right, 58 moves for the medium test. Then let's conduct the for near impossible. For the near impossible test case, it is actually a test case which has a minimum of 51 moves to complete, which is a quite a hard game. Let's just try it. As you can see, hard games often actually a very um has a quite a long process. All right. So to prove it to you, I'll just conduct the test cases on random FreeCell boards that I encountered on the internet. That is the test boards right here. There's the second test board, as you can see over here. You see, that's the problem when you have an iteration that is so long just because you have found a local optimum that doesn't lead to the global optimum and it just wastes time processing over and over. All right, and the third case, I can prove to you that my freestyle engine is actually working. So we have conducted the test and we have successfully determined that this freestyle engine is valid. All right, let's go back to the paper. All right. Okay. So these are the statistics that I got after conducting those tests. You see, easy games are practically very easy from the point of view of the solver because it doesn't need to process much when you actually have puzzles that have a path length of less than 30 and it did. It just iterates very quickly. And the average nodes expanded are not too much actually. Now, the tough part comes in the medium and hard categories where some random variables can very much disrupt this FreeCell solver's iteration. Yeah, but overall, 95% of the tests I conducted has been successful. The test I mean is the tests I conducted before I made this video. So I really want to test the durability of the solver, right? There are certain scenarios that maybe still doesn't quite fit overall with the heuristic I made. But for 95% of the other cases, it does fit. The question is just when does it find the solution? And in the paper, I also inserted an impossible test case, which is pretty much a theoretically impossible game. I really wanted to know what the freestyle solver's iteration will be like. But after 60 seconds, it does not find, uh, it just stops right there because I have already implemented the stopper method, which stops after 120 seconds or 200,000 nodes visited. All right. Okay. So basically, the most important and most critical point of this paper, from my point of view, is although the standard A-star search in this FreeCell solver is not admissible, the great thing about it is that it actually accounts for the quite precise amount of weight between heuristics. So actually these heuristics, they pretty much are quite equivalent to each other, The best heuristic is the heuristic with the deserved most weight is, of course, the card-in-home heuristic, right? Then the second of all is we want to create card sequences. And then empty tableaus, we don't actually want to overuse FreeCells. And a penalty per block card heuristic equals to 1. Now, this heuristic actually means something when actually implemented and tested from the results before. And I think this actually already quite depicts on how the game strategies are like, Your first priority is to put your cards in home, right? But your second priority and your third priority is to organize these cards in a certain way that after being organized, they can easily support the first objective, to put the cards in home and to free up the cards without being blocked. So although these heuristics are not admissible, but at least these heuristics, they converge the searching space so that only certain moves that comply with the strategy are selected, Although there very may be a test case out there that has a solution path that does not comply with these heuristics. So although it's not admissible, it's actually a pretty efficient way rather than just randomly searching or broad first search, depth first search without any clue, or even the A-star search without any with just standard heuristics, although admissible, but the memory space is too big for it to search to actually find the solution in an effective time, You don't want to wait like 1 hour, 2 hours just for the solution to show up, although it is maybe the shortest path, So here, my toughest opponent actually is the fact that I still haven't quite find the shortest path yet, because the A-star algorithm was designed to find the shortest path, right? But for my paper, the A-star algorithm's functionalities is not the shortest path, but just to find a clear solution. It is actually quite useful for that too, For the conclusion, yeah, I pretty much have made the solver done, and the solver is very much, it can solve 95% of the puzzles, I can guarantee you that. And this project is original. All right, I think that's it for today, guys. So I hope you guys got some insight from this, and I think that's it for me. I don't know what to explain anymore in this paper. I have already described it previously. Thank you for watching. Have a very nice day.